Okay, so we had looked into VSATs, right, which is nothing but your virtual satellite, or we can even call it as very small aperture terminal system. Okay, very small aperture terminal system. So, we have seen the diagrams, right, where, this is the hub station. Okay, so we need a computer and we need a hub equipment, and these are, the individual receivers. Okay, the small receivers, the VSAT remote sites. Okay, so we can even term them as the local receivers, right? And these are nothing but the outdoor units. Okay, so whatever you see here, these are your outdoor units. So this outdoor unit is connected to indoor unit. Okay, and from indoor, okay, it gets into your user terminal. Fine. There is one disadvantage here. Uh, one outdoor unit cannot communicate directly with the other one, but then it has to go through a satellite. So that is one disadvantage of a VSAT, right? So we have seen that. So the initial cost is high, right? And the tendency towards optimizing the systems for large networks. So just imagine this was about 3 to 4 configurations, right? Now imagine if there is a huge network of about 500. Okay, so this is going to be a complex network. There is going to be a lot of hardware involved, because you need the outdoor unit, indoor unit, and individual computers for receiving the signals. So even though you're going to use a single satellite, okay, but then still it's going to be a complex task. Okay. Question can be asked with regards to VSAT. Okay, you can draw this diagram. Okay, this is a simple diagram, and you can mention the features. Okay, so the features, that's not going to be less than about 2.4 meters. Okay, and all those important, I've marked it in red. Okay, so then it should at least be about 1.5 meters. Okay, then VSAT is usually reserved for private networks. Okay, I think you would have heard of this VPNs, right? Virtual private networks. So usually, right, we employ this kind of systems, where private networks. Okay, you need to have a private channel of communication. So in that case, this VSAT comes into picture. Okay, right, and we can use this for bankings and financial institutions, because if they want to have their own private network and do not want to rely on the public network, okay, for the sake of security, for the sake of privacy, okay, and customers database, okay, keeping them confidential. So usually, they invest more money, and they will have networks which will actually support having all these extra features. Okay, so these are having, red dots and blue dots. Okay, so you can see the red dots is actually sending, and the blue dots is receiving. So as we all know, these antennas just don't send data, but they also send and receive information. Right, so we have seen this in a class, right, which is talking about the basic structure. It has broadcasting facility. Okay, so it's going to use a star type of configuration. Okay, a star type of configuration, and the hub station is operated by the service provider, and it may be shared among a number of users, but of course each user organization has exclusive access to its own VSAT network. So as I mentioned, right, they will have their own VSAT network. So the reason why they're doing that is, is because they need to have a proper, a stable network, right? If they don't have it, then there's no point in having an error free, because banking sector especially, right, you should make sure that there are no any kind of errors. Okay, I don't know how many of you all experienced, yesterday the network UPI, the Unified Payments Interface, it was down, and we were not able to make payments. Okay, that's because of some regular maintenances that happens. Okay, so in that scenarios, right, we have to make sure that our networks are really good. Okay, it is fail proof. Basically, it's fail proof. Okay, so time division multiplexing is the normal downlink mode of transmission from hub to VSATs. Okay, so TDMA is what we're going to use. Okay, from the hub. Okay, from the hub to VSATs. And the transmission can be broadcast for reception by all VSATs in network, or addressing or address coding can be used to direct the messages. Let's say, for example, now this is broadcasting, right? The satellite is broadcasting. Now you should make sure that this message. Now say I want to address this third outdoor unit. So in that case, we can put addresses, okay, and specifically make sure that that information is reaching whichever outdoor unit is specified for. Okay, fine. And yeah, so the access the other way from VSATs to hub is more complicated, and a number of different methods are used. TDMA is not efficient for low density uplink traffic. So keep this in mind. TDMA is not that efficient if you want to have a low density uplink traffic. So usually whatever requests that are sent to the satellite will be uplink, and whatever requests are received from the satellite is going to be downlink. Okay, so we need to make sure that this TDMA is is not that efficient. So make sure that we use something else apart from that. So we use something called DAMA, which is demand assigned multiple access. Demand assigned multiple access. Okay. So the traffic in VSAT network is mostly data transfer of burst in nature. So which means you will have this information bursting, okay, just like pulses. And being inventory control, credit verification, and reservation requests. See, when you're booking your flight tickets, okay, when you're booking some, or you're making some banking transaction, things should go in real time, right? If it's not in real time, then it cannot happen. Seriously, it cannot happen. And especially with regards to banking, right? In banking sectors, you cannot afford delays. You have to make sure that these transactions happen in real time. Okay, fine. TDMA mode can lead to low channel occupancy. So the usage of channels, okay, which means the bandwidth utilization is going to be very less when we are employing TDMA kind of network. So a form of DAMA, okay, which is nothing but demand assigned multiple access, is employed in some systems in which channel capacity is assigned in response to fluctuating demands of VSAT. So here we have the facility, okay, to vary the capacity of the channel, and according to the traffic, okay, according to the traffic, it is allocated. So I've put up a lot of information here with regards to VSATs, right? And so CDMA is one such technique, okay? And there's something called Aloha Protocol, okay? Aloha Protocol. So CDMA along with Aloha Protocol, I want to have a look at this protocol, okay? And you can actually know why is this better. I've put up few information here about the protocol, right? The basic Aloha method is a random access method in which packets are transmitted at random in defined time slots. So you have a specific time slot, and these packets are directed to whichever unit that has to receive. Let's say, for example, from this satellite, I want to direct the information only to this middle outdoor unit, possible, right? So addressing, we have to give a proper address, and this information can be directly sent to this because it's a kind of addressed mode, okay. The others wouldn't receive it, okay. So it's like we are directing the information to an outdoor unit, okay, right. The system is used where the packet time is small compared with the slot time, and provision is made for dealing with packet collisions which can occur uh, with packets sent up from different VSATs. Okay, so this takes care of even packet collision. See, sometimes what happens, maybe you're on a call and you can actually hear your own voice. That happens because of the impedance mismatch. So if the impedance both at the transmitter and the receiver are made the same, okay, so this kind of issue wouldn't happen. So similarly here, since we are sending information in bits and pieces, right, which means we are making packets. So this packets has bits of information, and these packets are sent from one point to another point, right? We have to make sure that these packets are not lost, because if packets are lost, that means you're losing data. Sometimes you would have seen, you say your voice is breaking up. That's because few of the packets are lost, right? So that communication doesn't become a reliable one, okay, but then it becomes an intermittent one. Abraham calls this method spread aloha and presents the theoretical results which show that the method provides the highest throughput for small earth stations. So whatever we do, right, we want to get them in the form of numbers, right? We want to make sure that we have the best signal, okay, so that there's no much of loss happening. Okay, then some more information. Gamma can be used with FDMA as well as TDMA. So that is one, bridge. It acts like a bridge between the frequency type of division and time division multiple access. Okay. The disadvantage of the method is that reserve channel must be instituted through which VSATs can make requests for channel allocation. So you should plan how much your channel is going to be, the capacity of the channel. Okay, and this is going to use the star configuration. VSATs, they can operate in star configuration. This requires a double hop circuit with a consequent increase in propagation delay, and twice the necessary satellite capacity is required compared with a single hop circuit. So since we are allocating bandwidth, right, since we are allocating how much my channel has to keep, okay, the capacity of the channel, so many things have to be planned beforehand, okay, and then start the communication. So that's one downside. In Hughes, a proposal is presented for VSAT system, which provides for mesh connection, where VSATs can connect with one another through the satellite in a single hop. Okay. So using single hop, okay, which means from one point to another point, just with a single hop, we are able to connect. Most VSAT system operate in KU band. Now, as you all know, KU band, is having 14 gigahertz of uplink and 12 gigahertz of downlink, right? Here, so KU band, most of the satellites, see, any satellite that comes into picture, right? We need to operate them at a higher frequency because the distance is far, right? So lower frequency wouldn't actually suffice. Although there are some C-band systems in existence, so this C-band is usually used for terrestrial networks. And the other important thing here is, with regards to the effective area, right? So when I say this effective area, it is coming down to lambda by d constant. Okay, so this is nothing but the wavelength, and d is nothing but the diameter. So depending on these two factors, right, we make sure that the effective aperture, okay, it plays an important role in receiving and transmitting a signal. The satellite antenna gain is therefore constant, and given for high amplifier output, the satellite EIRP remains constant. So as much as possible, we want to make sure that the EIRP remains constant. For a given size of antenna, right, we make sure that the Earth station for a fixed EIRP from the satellite and received power at the Earth station is independent of frequency. So we make sure that it is independent of frequency, so that as we saw in the previous section, if we want to use C band or if we want to use KU band, because it's very much dependent on the frequency, right? So in that case, if I can change the frequency, right, it's not going to have much of an impact. Okay. This ignores the propagation margins needed to combat atmospheric and rain attenuation. So we have seen this exclusively in our initial lectures where the attenuation can happen because of the atmosphere. So in short, we can even call them as atmospheric absorption, AA, right? And we have the attenuation, which is caused because of the rain. Now, because of rain, there can be a cold temperature, and there can be a cloudy atmosphere, right? Because of which there can be ice formation, right? All these are contributing factors for signal loss. The necessary fade margins are not excessive for K band VSAT system, and the performance otherwise is comparable with KO band. So there's another band called K band. Okay. I want you to refer to my notes. Okay, I have mentioned previously what regions or what frequencies they fall in, right? Okay, so I could ask you what is the shortcomings of VSAT. So the initial you know initial cost, the investment is high, okay, but the maintenance is fine, provided you have a small network. If you have more than 500 VSATs, then it becomes a little clumsy work to actually connect them all. Lack of direct VSAT to VSAT, as I mentioned, right? So it has to go through a satellite, and there's no direct connection between them. Technological improvements, especially in the areas of microwave technology and digital processing, will result in VSAT systems in which most, if not all, of these shortcomings can be overcome. So as we know, day by day, there are a lot of enhancements, technological enhancements. Previously, we used to work with, micrometers, right? And now we are in nano, right? So nano is again still coming down, where you have processors these days having 5 nanometer, 3 nanometer, right? So we're actually moving out of nanotechnology, and there's a lot of enhancements happening in the world of technology. So the thing here is whatever is the shortcoming, okay, can be overcome with technology's maturity. So next is about Radarsat, right? So Radarsat is a radar satellite, okay, is an Earth resource remote sensing satellite, which is part of the Canadian space program. So they brought up this Radarsat, and this was launched in the year 95, okay, and the second version was in 2006. So usually, it takes about 10 to 15 years for a satellite to be successfully researched and launched and put up in the orbit, and after which it can be taken into service for about 15-20 years, and later on, once the performance goes down, okay, we we stop using it, or we probably move it into the uh, graveyard. And those are called satellite graveyards. So let's move on with the objectives. So there can be a question based on the objectives. I can ask, what are the objectives of Radarsat? Why was it actually brought into? Okay, a concept with SAR, okay, synthetic aperture radar. So radars were actually playing an important role, especially in the World War. During the World War, they wanted to know, what kind of is it a friendly object or an enemy object, right? So radars play a very important role in identifying, because borders are guarded, okay, even the air base are guarded. Okay, suppose there's no support from the neighboring countries, okay, let's say you're planning a travel from point A to point B, and that passes through various countries. Okay, so if in case there is no proper uh, understanding, let's say this is point A, okay, and this is point B, okay, and you want to actually travel from point A to point B, and here you have lot of countries coming in between, right? So if in case, these countries do not allow their airways, then, you may have to take a different route, right? You may have to probably, move from here, and then, probably from here, and then you have to come down here, okay, and then finally reach your B, right? So it really becomes a very, problematic situation, okay, where, your travel time has increased. Not only that, it's a national waste because you are, spending a lot of money on fuel, right? So uh, so this radar sat, helped us in understanding which which flight or which object is friendly, okay, which is an enemy. So, those were targeted. Okay, so information is passed that, this flight is moving from point A to point B and passing through these countries. So all the information keeps broadcasting, right? So that's how it works. So this provides application benefits for resource management and maritime safety. So it develops, launch and operate an Earth station observation satellite with SAR, and establishes Canadian mission control facility. Okay, so that was their main idea. Okay, and market Radarsat data globally through a commercial distributor. So they wanted all the countries to actually adopt this technology, which is Radarsat. Make SAR data available for research. Okay, so usually, what happens now. Let's say we want to predict weather on Mars, right? So we cannot expect all the countries to launch their satellites and start mining data from Mars, right? So instead, if few of the countries, have launched, then probably the other countries can go with an understanding, with an MOU, sign an MOU, and, they can actually take the data which has been extracted from their satellite. So in this way, they're saving time, they're saving money, and they're saving the maintenance costs. Okay, so many things comes into picture. So they wanted to map Antarctica in 2 seasons and map the whole world in a stereo radar. So that was the idea. Applications, major, it's only for mapping, right? So it can be, the forest management, how many trees were there, and then what was the density of the forest, and then after some time what happened, were the trees cut down, as the years, using a time lapse, right? They'll be able to measure, and they'll be able to analyze these images taken by satellite, okay, to make sure that these forests are guarded. It can be even with regards to lakes, rivers, okay. Sometimes what will happen, these lakes might be encroached, okay. So using satellite data about 100 years, okay, or about 75 years back, right? So you will be able to exactly know where the lake was exactly, and accordingly you can guard this lake. So satellite, it really plays an important role in, guarding this information and helping us in many of the applications. All right, so this Radarsat satellites has LUs, okay, which means they are launched in low Earth orbits. So the altitude is about 800 kilometers, right? Inclination is about 98.6 degrees, and the period, okay, it takes about 100 minutes, and the repeat cycle, it happens once in 24 days. Okay, so when a question is asked with regards to Radarsat, you can include these technical information as well. Okay, the orbital parameters are similar to those for the NOAA. Okay, so in short, it's called NOAA. So which means National Oceanographic and Atmospheric Administration. So this body takes care of the information with regards to ocean and atmosphere. In particular, the Radarsat orbit is sun synchronous. So it is in sync with the sun's movement. Okay. It carries only C-band radar as the sensing mechanism. So these satellites carry a wide variety of instruments, Although it is known that C-band radar is not optimal sensing mechanism for the applications, the rationale for selecting it is that it operates in darkness. Now, this is important, right? So usually when we adopt a technology, right, we look at its advantages and disadvantages. So if the advantages are higher compared to the disadvantages, then we will go for it, even though there are few disadvantages. So the highlight of having a C-band type of radar is that, it can operate in darkness. Now this is important, right? And it does penetrate cloud cover, smoke, so it can just pass through. So it's visible. So there's nothing, literally there's nothing that can block the vision of the satellite. Much of the sensing is required at high latitudes where solar illumination of the earth can be poor and where there can be persistent cloud cover. So for example, places like Antarctica, these are always cold and snowfall. Okay, it's all snow covered. So even the beds, the seabeds there are all frozen. Okay, so in that case, when you want to sense, when you want to do a remote sensing, okay, so this kind of C-band radar is actually helpful. Now there is a concept called dawn to dusk. Okay, so what is it? The orbit is described as dawn to dusk, which means that the satellite is in view of the sun for the ascending and descending passages. So which means you can actually see the satellite, the orbit, okay? The satellite is in view of the sun. Okay, so the sun and satellite during the ascending and the descending, okay, it is visible. So this is called dawn to dusk. Fine. With the radar sensor, it is not necessary to have Earth illuminated under the satellite. In other words, the sun's rays reach the orbital plane in a broadside fashion. So the sun rays are actually able to reach the satellite's orbit. So that's what it means from dawn to dusk. The main operational advantage is that the radar becomes fully dependent on solar power rather than battery power for both ascending and descending passages. So which means, there is always the solar cells can be utilized, okay, because it's in the vicinity of sun's rays, okay, and they almost never have to use the battery power, which is really good, right? See, because this is not about 40,000 kilometers, it's not placed about 36 to 40,000 kilometers, but then it's just about 800 kilometers altitude, right? So that's the advantage. Since there is no operational need to distinguish between the ascending and descending passes, nearly twice as many observations can be made than otherwise would be possible. So we can make more number of observations, okay, with this kind of setup. So the downlink periods for data transmission from Radarsat will take place at times well removed from those used by other remote sensing satellites. Okay, so this data is reliable and it can be utilized. Further advantages stated by the Canadian Space Agency are that the solar arrays do not have to rotate. The arrangement leads to a more stable thermal design for the spacecraft, and the spacecraft design is simpler, and it provides for better power raising capabilities. Now, I think you would have heard of the latest, satellite which was able to touch the sun's surface, right? So that was called the Parker. So if you can imagine the complexity involved in getting this to touch the sun's surface, right? For the first time in human history, this is happening, right? So which means this is a very remarkable landmark, okay, in the pages of human history, right? So which means think of the type of materials, think of the type of testing, think of the type of the environment that they should have created, okay, on Earth here before getting it manufactured on a larger scale, right? So with this particular dawn to dusk orbit, the satellite will be eclipsed by the Earth in southern hemisphere from May 15 to July 30. So there's going to be a little bit of eclipse, okay, from May 15 to July 30 is the only time where there's going to be eclipse. The eclipse period changes gradually from 0 to a maximum of about 15 minutes and then back to 0. So which means you can see that, this eclipse can start, okay, can have a minimum of about 0 minutes and it can go to a maximum of about 15 minutes. So as we have seen, right, the maximum eclipse can last for about 72 minutes, right? That's what the maximum recorded thus far. So 15 minutes is actually not such a big deal, and these batteries are made sure that at least they cover for about 80 to 90 minutes, okay, and once it gets back the sun's rays, the batteries automatically charge and they are back on solar power. The battery backup consists of 50 ampere nickel cadmium batteries, okay. So uh, there's a lot of R&D that happens in the field of batteries, lithium ion, lithium polymer, nickel cadmium. Okay, so these are all reliable materials which can be used for constructing batteries. And the other thing is, the quality should be of high standard, okay, because you cannot go there to the space and get the batteries replaced frequently, right? Not possible. So the only way to do it is, research properly and make sure that, before sending it on the space, okay, you have the best quality installed. Fine. So now if you see this, okay, this is the time of the year and the duration of the eclipse, right? So as I mentioned, from May 15 to July 30. And if you can see here, right, maybe let me just draw a line. Okay, right. So maximum, it's about 15 minutes that, we're going to see the eclipse. Okay, and that's fine. That's fine. So we are ready to handle that kind of situation. So this is a simple aircraft, okay, a Radarsat spacecraft configuration where these are the panels, as you can see, the solar panels, and this is the bus module, okay, which means the vehicle which actually takes them, and this is your SAR, okay. So SAR you have seen previously, right, and the payload module actually stays inside, and these are the antennas, right. Um, Plays a very important role here, the antennas, in receiving and transmitting. This is one of the configurations. Okay, so this is the spacecraft configuration as we saw, right? And as I was mentioning, this antenna plays a very important role. So Radarsat is comparatively large spacecraft. The total mass is about 3,100 kilos. The radar works at a carrier frequency of about 5.3 gigahertz, which can be modulated with 3 different pulse widths and depending on resolution requirements. So you have the option to change the resolution, and if the resolution needed is high, then the operating frequency also does change. Okay. The SAR operating modules, okay, modes are shown in this diagram. Okay. Now let's say, okay, the satellite path is here. Okay. So these are going to be the standard beams, which are also called as spotlight beams. So it can track this much of area. Okay. And this is in the 500 kilometer range. Okay. And this is 300 kilometers. And next, say I need a wide beam. Okay. So, so you can see that the area covered is higher. Okay. Next, I need a fine resolution, okay, which is much smaller than standard beams. Okay. Then the satellite again, the distance changes. Okay, the distance changes, and I have a scan SAR. Okay. Then these are some experimental beams that can be launched, right? So you can see that there are different sections here, right? So which means this satellite is a very complex thing where it can change the way in which, you know, we can track things, right? Okay. As shown, different beam configurations can be achieved giving different resolution. The satellite completes 14 and 7 of 24 revolutions per day. Okay. So some of the more information uh, when it's operational, okay, how much of kilometers that it's covering, what is the resolution, and the incidence angle and the degrees, the high resolution. Okay, so which means, you know, it's the swath, okay, the swath, the area, then experimental, then scan. Okay, so you have different angles, four looks, which means four different angles in which you can see that. Okay, so some of the different modes of operation. Okay, so now I want you to study GPS and ORBCOM as well. Okay, so that is available in your textbook, your prescribed textbook, and I have mentioned that in the syllabus, okay, from which section that it could be picked up. Okay, so with this we actually complete module 5. Okay, and we are left out with few more information, you know, probably about half module with in module 4, okay, which talks about the CDMA and FDMA techniques. Okay, so just give me a moment, we will switch on to that. Okay, so in module 4 we have satellite access techniques, right? So this is what we'll be looking into right now. So the first thing that we need to know is bandwidth limited and power limited. How are they related? There are quite a few equations that we need to look into, right? And we will see them one by one. A transponder will have a total bandwidth of BTR. I will just give an introduction to this topic, and then probably in our next class, okay, we'll be looking into FDMA downlink analysis, where we have few equations involved, right? The required carrier to noise ratio, okay, all those stuff. So for today, we will just look into the introductory part of it. So a transponder will have a total bandwidth. Okay, so we term it as BTR, and it is apparent that this can impose a limitation on the number of carriers that can access the transponder in an FDMA mode. So as we saw previously, okay, we were using in VSAT TDMA, and then we moved on to DAMA, and then we moved on to the implementation of Aloha Protocol. Okay, uh, uh, along with this transmission technique, right? Fine. For example, if there are k number of carriers and each is having a bandwidth of capital B, always bandwidth is represented with capital B, then the best that can be achieved is k is equal to BTR, which is the total bandwidth divided by bandwidth required by each carrier. Okay, so any increase in the transponder EIRP will not improve on this, and the system is said to be bandwidth limited. So which means I am tied to this value. I'm tied to this k. K is equal to BTR by B, where BTR is nothing but the total bandwidth. Likewise, for digital systems, the bit rate is determined by the bandwidth, which will again be limited to some maximum value by BTR. Okay. Power limitation occurs when EIRP is insufficient. See, we know that many things are combined, right? We know that EIRP is there. Okay. We know that uplink frequency is there, downlink frequency is there. So many things are connected. So if things work in tandem, okay, if things work together, okay, it's only then we will be able to achieve a successful communication. If not, then it's going to be impossible. Okay, because we need to think of this carrier to noise ratio as well, right? The signal bandwidth will be approximately equal to the noise bandwidth, and if EIRP is below a certain level, the bandwidth will have to be correspondingly reduced to maintain the C by N ratio at required value. So what I'm trying to say here is EARP value, C by N ratio, okay, the uplink frequencies, downlink frequencies, okay, the gain of the antennas, of the transmitting antenna, of the receiving antenna, all these parameters are to be kept in mind if we want to have a successful communication. Okay, so in our upcoming class, okay, we will be looking into FDMA downlink analysis. We'll be seeing few equations, and we'll try to analyze, okay, how this actually works. Okay.